Welcome to Deep Space Intelligence. My name is Liam, and this is the channel where we take the biggest questions in space science seriously, research them carefully, and bring you the findings in a way that actually makes you feel the weight of what we're discovering out there. Whether you're a lifelong astronomy enthusiast, or someone who simply looked up at the night sky one evening and found yourself unable to look away, this channel exists for you. Thank you for being here tonight. We are going to the moon, not in the way the history books describe, not in a capsule with astronauts and mission patches and flags pressed into powdery regolith. We are going there to look at a wound, a fresh wound, ripped open in the spring of 2024, sitting there on the surface of our nearest neighbour in the solar system. A wound that nobody saw being made. A wound that sat there for months, undiscovered, while the Earth kept turning and the sun kept rising and the moon kept hanging in the sky like it always has, ancient and silent and seemingly unchanging. And then, on a routine review of satellite imagery, a scientist noticed something different. Something that wasn't there before. A scar, perfectly round, brutally deep, surrounded by pale debris thrown violently outward in all directions, like the aftermath of an explosion frozen in time. Because that is precisely what it was. Scientists identified a new crater on the moon that formed in the late spring of 2024, revealing the violent aftermath of a recent collision on the lunar surface. The discovery was made using images captured by NASA's Lunar Reconnaissance Orbiter, a spacecraft that has been quietly circling the moon since 2009, photographing its surface with extraordinary precision. The team analysed changes between before and after images of the same region, piecing together the story of an impact that happened without warning, without witness, and without any prior detection of the projectile responsible. The findings were presented at the 57th Lunar and Planetary Sciences Conference in March 2026. And the numbers, when they sank in, stopped scientists cold. The newly discovered crater measures around 738 feet across the lunar surface, making it the largest impact crater to have formed during NASA's LRO's 17-year mission. That is 225 meters of fresh, gouged-out lunar rock. To give you a sense of the scale, picture 2 football fields placed end to end. That is the width of this scar. Before this discovery, the largest crater found to have formed during the entire LRO mission was just 70 meters across. This new crater is more than 3 times that diameter. Let that sink in for a moment. 17 years of watching the moon. Thousands upon thousands of orbital passes. Millions of square kilometers photographed in high resolution. And the biggest fresh crater ever documented on our satellite is this one, discovered just weeks before I'm recording this script. Science has a way of humbling you just when you think you've got something figured out. An impact of this size is only expected to happen once every 139 years, based on existing models. That is not a geological timescale. That is not the kind of number astronomers use when they talk about ancient bombardments and deep time. That is a number that fits within recorded human history. The last time a rock struck the moon and carved a hole this large in that particular patch of ground, there were people alive who had never heard of powered flight, and nobody saw it happen. To understand why that matters, and why scientists are not just documenting this crater but actively monitoring what happens to it next, we need to go back to the beginning of the story, not to April or May of 2024, when the impact occurred, but to the very formation of the moon itself, because the crater is not just a hole in the ground. It is a chapter in a story that started 4.5 billion years ago, and it is still being written right now. The moon, as best as current planetary science can establish, formed from the debris of a catastrophic collision between the early Earth and a Mars-sized body called Theia. That event, approximately 5 billion years ago, blasted an enormous quantity of material into orbit around the young Earth. Over time, that material coalesced under gravity into the body we now call the Moon. It was born from an impact. In some deep poetic sense, craters are not just features of the Moon, they are its heritage. They are the signature of the same violent process that brought it into being. For much of the next several 100 million years, the Moon endured what planetary scientists call the Late Heavy Bombardment, a period of intense asteroid and comet impacts that scarred its surface so thoroughly that the marks from that era are still visible to the naked eye from Earth. Those dark regions you see when you look up at a full moon, the patches that people have for millennia interpreted as the features of a face, are not mountains or craters in the traditional sense. They are ancient impact basins, some of them thousands of kilometers wide, later flooded with dark basaltic lava that welled up from the Moon's still hot interior. They are called maria, from the Latin word for seas, because early astronomers mistakenly believed they might be bodies of water. They are not. They are the scars of collisions so massive they reshaped an entire world. That era of catastrophic bombardment ended roughly 8 billion years ago. Since then, the Moon has been quieter, though never entirely still. Smaller objects, asteroids, comets, and the constant drizzle of micrometeoroids that pervades the inner solar system have continued to pepper its surface at a lower but unceasing rate. Every crater you see on the Moon is a record of one of these events. Every ring, every ray, every boulder field radiating outward from a central depression represents a collision that happened somewhere in the vast timeline between then and now. The Moon has no atmosphere to protect it. On Earth, most incoming rocks burn up in our atmosphere before they reach the surface, heating the air around them to thousands of degrees and disintegrating into harmless sparks of light that we call meteors. The Moon has no such shield. Every rock that approaches it, from the smallest grain of sand to a boulder the size of a building, strikes the surface directly. Nothing is filtered. Nothing is slowed. The Moon absorbs everything the solar system throws at it, and it carries every one of those collisions as a permanent scar. This is why the Moon's surface looks the way it does. It is not simply old. It is a record. A 4 billion year archive of everything that has passed through this neighbourhood of the solar system, written in rock and regolith, and the slow chemistry of a surface that has been baked by solar radiation and bombarded by charged particles for longer than complex life has existed on Earth. And here is what makes the 2024 discovery so scientifically valuable. By carefully comparing images taken years apart, scientists can detect newly formed craters and study how fresh material gradually darkens under the effects of space weathering. That process, the gradual darkening and chemical transformation of fresh lunar material, is one of the most important tools planetary scientists have for dating surfaces across the solar system. Understanding how quickly newly exposed material changes tells us how to read the age of terrain on other worlds. The 2024 crater gives researchers something extraordinarily rare. A known starting point, a precise timestamp for when a fresh surface was created, combined with the high-resolution imagery needed to watch what happens to it over time. Before we go deeper into the science of what is being observed now, let us talk about the spacecraft that made this discovery possible, because without it, none of this would be known. The Lunar Reconnaissance Orbiter is a NASA robotic spacecraft currently orbiting the Moon in an eccentric polar mapping orbit. Launched on June 18, 2009, in conjunction with the Lunar Crater Observation and Sensing Satellite as the vanguard of NASA's Lunar Precursor Robotic Program, LRO was the first United States mission to the Moon in over 10 years. Its primary purpose was practical: to map the Moon's surface in enough detail to identify safe landing sites for future human and robotic missions. But in the 17 years since its launch, it has become one of the most scientifically productive missions in the history of lunar science. The overarching goals of the LRAC investigation include landing site identification and certification, mapping of permanently polar shadowed and sunlit regions, meter-scale mapping of polar regions, global multispectral imaging, a global morphology base map, characterization of regolith properties, and determination of current impact hazards. That last item, current impact hazards, is exactly what the 2024 crater speaks to. The two narrow-angle cameras are monochrome narrow-angle line scan imagers, capable of resolving features at 0.5 meter per pixel from an altitude of 50 kilometers. To appreciate what that means, consider that the cameras aboard this spacecraft, circling the moon hundreds of kilometers overhead, can photograph features on the lunar surface small enough to fit inside a modest living room. When LRO passed over the Apollo landing sites, it could see not just where the lunar modules landed, but the scientific equipment the astronauts left behind, the footpaths they walked between instruments, and even the shadows of flags still standing in the unchanging vacuum. The LROTH investigation is led by Principal Investigator Mark Robinson of Arizona State University, with instruments designed and built by Malin Space Science Systems and operated at Arizona State University in Tempe, Arizona. Robinson is the scientist who presented the findings about the 2024 crater at the Lunar and Planetary Sciences Conference, and he has spent the better part of 2 decades systematically comparing older orbital images with newer ones, hunting for exactly these kinds of changes on the surface. The methodology is elegant in its simplicity. Take an image of a patch of lunar surface at one point in time, come back later and photograph the same patch again under similar lighting conditions. Compare the 2 images carefully, pixel by pixel if necessary, looking for anything that has changed. A crater that was not there before, a landslide, a boulder that has rolled, a subtle brightening where fresh material has been exposed. This methodology transformed understanding of lunar dynamics by proving craters form regularly during telescope-era observations, and between 2009 and 2016, unprecedented crater detection rates revealed an active collision environment with impact frequency higher than previously estimated. The Moon, it turns out, is being bombarded more frequently than scientists once believed. Before LRO, estimates of the current impact rate were based primarily on crater counting, examining the density of craters in various regions and working backward from models of how fast those craters should form. Those models were reasonable, but they lacked direct observational confirmation. LRO changed that. By catching new craters in the act, so to speak, detecting them shortly after they formed by comparing sequential images, scientists have been able to test and refine those models with actual data. The results were surprising. Scientists previously assumed the lunar surface remained geologically static on human timescales, but LRO observations contradicted this assumption, revealing more than 200 impact features identified during LRO mission operations. That is over 200 detectable impacts in roughly 16 years of observation from a spacecraft that only photographs a fraction of the total surface on any given orbital pass, and only sometimes catches a crater shortly after it forms. The true rate of impacts is almost certainly higher. Now here is the thing about the 2024 crater that sets it apart from those 200 earlier discoveries. Size matters in this context, and not just for the obvious reason that a larger crater is more dramatic. Size determines what kind of science you can extract from an impact. Smaller craters, the kind measuring a few meters or a few tens of meters across, are informative but limited. They tell you an impact occurred, they tell you roughly how much energy was released, and they give you a small patch of freshly exposed material to study. But they do not give you the full picture of how the cratering process unfolds in lunar bedrock. The 2024 crater is different because of what the numbers reveal about the impactor and the impact process itself. The crater is funnel-shaped, 43 meters deep, with steep walls, and inside the crater, the team found areas of unusually dark material, almost certainly glassy rock, flash melted by the colossal heat of impact and then instantly solidified, which is the fingerprint of a collision that released more energy in milliseconds than it is possible to imagine. Let us think carefully about what those glassy rocks actually represent, because they are one of the most scientifically fascinating details of this discovery. When a space rock travelling at many kilometers per second collides with the Moon's surface, the energy of that collision is released almost instantaneously. The numbers are difficult for the human mind to fully grasp. A rock travelling at, say, 20 kilometers per second carries kinetic energy proportional to the square of its velocity. Double the speed, and you quadruple the energy. The collision does not behave like a slow mechanical process. It behaves like an explosion. When an impactor contacts the Moon's surface, it compresses, pulverizes, and vaporizes the rock beneath it. That material then rebounds, and the energy of the rock decompressing sends shockwaves racing outward through the surface, melting some of the rock if the pressure becomes high enough. Material shoots upward and outward, and this spray of pulverized rock is called ejecta. The temperatures generated at the point of contact can reach tens of thousands of degrees Celsius, far hotter than the surface of the sun. Rock that was solid a moment before becomes liquid, and then becomes glass as it cools with extraordinary speed in the frigid vacuum of the lunar environment. There is no air to carry heat away slowly, no convection to moderate the temperature gradient. The material goes from a molten state to a solid glassy state in a fraction of a second. The resulting material, sometimes called impact melt glass or shock glass, is chemically distinct from the surrounding regolith and carries within it a record of the extreme conditions under which it formed. Impact glasses found in lunar soils provide a possible window into the impact history of the inner solar system, though their use for precise reconstruction of this history is limited by an incomplete understanding of the physical mechanisms responsible for their origin and distribution. The Apollo astronauts returned samples of such glass from the lunar surface decades ago, and scientists have been studying them ever since, using sophisticated isotopic dating techniques to establish when various impacts occurred. But those glasses came from ancient craters, their ages measured in millions or hundreds of millions of years. The glasses inside the 2024 crater are just months old. They are, in the vocabulary of lunar geology, essentially newborn. This is one of the reasons scientists are watching this crater so carefully. It provides a baseline, a known quantity, against which all the subsequent changes can be measured. How quickly does the glassy material at the bottom of the crater change under the influence of solar radiation and the solar wind? How fast do the bright rays of ejected material surrounding the crater begin to darken? At what rate does the sharp rim, so crisp and defined in the first post-impact images, begin to soften as micrometeorites gradually erode it? All of these questions can now be addressed with real data from a real crater whose birthday is known. The shape and orientation of the crater itself also carries information. The crater's steep walls and 43-meter depth indicate it struck solid, hardened material, while its slightly stretched shape hints that the subsurface is not uniform. A perfectly circular crater indicates a high-angle impact, essentially a rock coming straight down. A more elongated shape suggests an oblique trajectory, a rock that came in at a shallower angle, like a stone skipped across water, but in this case skipped into solid rock at extraordinary speed. The asymmetry of the ejecta pattern adds further information. By observing the images captured by LRO, the team was able to observe the direction of the debris and pinpoint where the impact originated, with the space rock appearing to have arrived from the south-southwest direction, travelling fast enough to puncture through the surface and spray a trail of debris northward. That directional information is significant. It tells scientists not just that something hit, but something about the trajectory of the impactor as it approached, which, in turn constrains what kind of object it likely was, and where in the solar system it originated. Most of the rocks that strike the Moon are not pristine asteroids on their first close approach to the inner solar system. They are fragments, chips knocked off larger bodies by previous collisions, or rocks that have been gradually nudged into Earth-crossing orbits over millions of years by the gravitational tugs of the larger planets. The Highland-Mare boundary, where this crater formed, is also scientifically relevant. The lunar pit lies at the boundary between two distinct lunar regions, the rugged highlands and the smoother mare plains formed by ancient lava flows, and this location helps explain its physical characteristics, with depth averaging around 43 meters and steep edges suggesting formation in strong solidified material, such as cooled lava. Highlands and mare regions have very different geological histories and very different surface properties. The highlands are older, more heavily cratered, and composed primarily of a calcium-rich rock called anorthosite. The maria are younger, darker, and made of iron-rich basalt that welled up from the lunar interior and flooded ancient impact basins billions of years ago. A crater that forms right at the boundary between these two geological provinces carves through materials with different mechanical properties, which is why the shape of the crater is not perfectly symmetrical. The structure beneath the surface was not uniform, and the crater's shape preserved a record of that non-uniformity. The depth, about 43 meters on average, and steep edges suggest the crater formed in strong material like solidified lava, which is consistent with its position at the mare edge. Now, before we go any further, I want to pause for a moment and say something that I think matters. At Deep Space Intelligence, we take the science seriously. We read the papers, we check the numbers, we look at what the researchers actually said, rather than just the headline. But science is a process, not a verdict, and the findings we are discussing here, while solid and well documented, are still fresh. The data is still being analysed. New papers are still being written. I would always encourage you to go and read the primary sources, look at the conference presentations, and form your own assessment of what the evidence means. The links and references will always be available to you, and the most honest thing any science communicator can tell you is to verify what you hear. With that in mind, let us return to the crater. There is something unsettling, in the best possible scientific sense, about the fact that nobody saw this impact happen. We live in an era of unprecedented surveillance of the sky. Professional observatories on every continent scan the night sky looking for near-Earth objects. Amateur astronomers with backyard telescopes photograph the Moon regularly and report any changes they notice. Space agencies maintain dedicated planetary defense offices, and yet a rock large enough to carve a 225-meter crater on the Moon arrived without warning, struck without being observed, and was discovered only through the painstaking comparison of before and after satellite images. That is not a failure. It is an illustration of the scale of the problem. The solar system is unimaginably large, and the objects moving through it are often dark, fast-moving, and small enough to escape detection until they are very close to their destination, if they are detected at all. The rock that created the 2024 crater was not tracked before impact. We do not know its exact size, though the dimensions of the crater it left behind allow scientists to make informed estimates working backward from what is known about the physics of impact cratering. It is a rare event that, according to models of how often impacts of this scale occur, should happen only once every 139 years on any given patch of lunar ground. This emphasis there is on any given patch. Averaged across the entire surface of the Moon, similar scale impacts happen more frequently. But for the specific area where this crater formed, once in a century and a half is the statistical expectation. The discovery process itself is worth examining in detail, because it illustrates how planetary science works in the modern era. It is not a single dramatic moment of revelation, but a methodical process of comparison, analysis, and confirmation. Scientists did not witness the impact itself. Instead, they identified the fresh scar after it had already reshaped part of the lunar terrain. The LRO camera was not pointing at that particular spot at the moment of impact. Even if it had been, the camera's field of view covers a relatively narrow swath of the surface on each orbital pass, and the chances of being in the right place at the right millisecond are vanishingly small. Instead, what researchers do is build up a library of before images over time, essentially photographing the entire surface repeatedly so that every region has multiple reference images from different epochs. Then, systematically and increasingly, with the help of automated detection algorithms, they compare the before images with newer images, looking for discrepancies. A fresh crater, with its bright ejecta rays and sharp rim depression, produces a very distinctive signature in this kind of comparison. The new scar does not match the old image. The difference stands out. This is exactly how the 2024 crater was found. Routine image comparison, conducted by a team that has spent years developing the techniques and the software to do this efficiently, revealed a feature that was simply not present in earlier photographs of the same location. The team then went back through the temporal sequence of available images to constrain when the crater formed, narrowing the likely window to the late spring of 2024. The fact that it took months or more to be discovered is not surprising given the scale of the monitoring challenge. Logic dictates that if the moon had been slammed into by a space rock, big enough to leave an imprint noticeable by satellite imagery, we would have noticed it sooner. But the truth is, it is hard to keep track of every square inch of the moon, and there are a lot of craters on it, with new ones not necessarily sticking out any more than the old ones, unless you have a keen eye and know what to look for. There is something philosophically interesting in that observation. The moon's face is so saturated with craters, layer upon layer of them accumulated over billions of years, that a new one of this scale can sit there undiscovered for months. The surface is, paradoxically, so rich with the evidence of past violence that the signature of recent violence gets lost in the noise. It is like trying to spot a new scratch on a surface that's already covered with thousands of scratches. The ejecta pattern around the crater deserves particular attention, both for what it tells scientists and for what it looks like in the imagery. When the impactor struck and the cratering process unfolded in those first few milliseconds, material was launched outward at high velocity in all directions, not uniformly, because the impactor came in at an angle, but in a pattern shaped by both the energy of the collision and the angle and direction of approach. Some of that material was launched at speeds well above the lunar escape velocity of about 4 kilometers per second, meaning it left the moon entirely and dispersed into space. Most of it, however, fell back to the surface, within a relatively short distance of the impact point. Surrounding the crater are massive blocks of rock that were ejected from the impact, with the largest one measuring at 42 feet, which is roughly 13 meters. And the team also noticed unusually dark material that resembles glass-like rocks inside the crater, which may have been melted by the heat from the impact before instantly solidifying. A 13-meter boulder ejected by the force of the impact and deposited on the lunar surface nearby. Think about the scale of that for a moment. A chunk of rock larger than a 3-story building, torn from the lunar ground by the violence of the collision and thrown outward before coming to rest in the ancient dust. And that is just the largest block the cameras have resolved. Surrounding the crater in all directions are countless smaller fragments, ranging down to sizes too small for the camera to detect, individually but collectively brightening the surface in a halo around the impact point. That brightness is one of the most diagnostic features of a fresh lunar impact. The intense radiation and impact environment of space changes the composition of the thin upper layer of the Moon over time, causing it to darken. And just underneath that is fresher, brighter material. When a crater impact throws up ejecta, it splashes that material onto the surface, and that becomes a crater ray, meaning the brightest visible rays on the Moon were created by the most recent impacts. This is the central insight that makes fresh craters so scientifically useful. The surface of the Moon is dark because it has been processed by space weathering. The combined effects of solar wind bombardment, micrometeorite impacts, and cosmic radiation acting on exposed material over thousands to millions of years. This processing creates tiny particles of nanophase iron embedded in the surface grains, darkening and reddening the material in a way that is measurable from orbit with the right instruments. Fresh material, dug up from below the darkened surface layer and deposited on top of it, is bright because it has not yet been processed. It is like turning over fresh soil, exposing the rich material underneath that has been protected from the surface environment. Over time, that freshly exposed material will undergo the same weathering process and gradually darken to match its surroundings. The bright rays that make young craters so visually striking, visible even to the naked eye in some cases, are essentially a timestamp. The brighter they are, the younger they likely are. Space weathering, caused by solar wind particles, micrometeorite impacts, and cosmic radiation, slowly darkens exposed material, and over thousands to millions of years, the crater's rays will fade until they blend in with older features. This process explains why ancient craters lack bright rays, while younger ones like Tycho, which formed about 108 million years ago, still display prominent streaks visible from Earth. Tycho is one of the most prominent craters on the near side of the Moon, easily visible with the naked eye from Earth as a bright spot near the southern highlands, with rays extending across enormous distances in all directions. The fact that those rays are still bright enough to see from Earth, 108 million years after the impact, tells you something profound about how slowly space weathering works on the Moon. The 2024 crater, by contrast, is just over a year old at the time of discovery. Its rays are presumably blazingly bright in comparison. But here is the twist that recent research has introduced, and this is where the science becomes genuinely surprising. New craters on the Moon are fading faster than expected, reshaping how scientists read surface age, with near the crater rim brighter and darker zones telling a different story from the distant rays, and blue-sensitive images showing cleaner subsurface grains in bright zones, meaning impact excavation lifted less weathered material upward. Some new craters, it turns out, are darkening faster than the standard models predicted. The details of how ejecta interacts with the existing surface layer, how the texture of the regolith changes around an impact, and how the mechanical disturbance of the impact itself affects the optical properties of nearby material, are all more complex than earlier models accounted for. Some zones near fresh craters look darker, not lighter, because the impact churned up mature, already weathered surface material and brought it to the top. This means that the simple rule of bright equals young and dark equals old, while broadly correct, is an oversimplification. The reality is more nuanced, and the more carefully you look at fresh craters with modern instruments, the more that nuance reveals itself. The 2024 crater, precisely because it is so large and so well documented, is going to be one of the key datasets used to refine these models. Scientists will watch its brightness evolve over the coming years and decades, measuring the rate of change with LRO's instruments, and use those measurements to calibrate their understanding of how quickly space weathering works at different scales. Far from the rim, some new craters made dark rays that suggest impacts reshape far more terrain than standard crater measurements alone would suggest. Lunar impacts do more than dig holes. They churn up the Moon's surface, disturbing layers of loose soil and broken rock known as regolith. Over time, that exposed material does not stay the same. This is the broader insight that the 2024 discovery is contributing to, an insight with practical implications that go well beyond academic interest in lunar geology. If we are going to send humans back to the moon, and the Artemis program is committed to doing exactly that, we need to understand the lunar surface environment with a level of precision that was never required for the brief Apollo visits of the 1960s and 1970s. The Artemis missions envision not just visits but sustained presence. A lunar gateway station in orbit, surface habitats, in situ resource utilization facilities, and eventually a permanent outpost at or near the South Pole. All of that infrastructure will exist in an environment that is being continuously bombarded by impactors of all sizes. The risk posed by micrometeoroids to spacesuits, habitat structures, and solar panels is already well understood and factored into mission designs. But the risk posed by larger impactors, the kind of rock that can carve a 225-meter crater, has to be understood in probabilistic terms. How often do objects of that size strike? Where on the lunar surface are impacts most likely? What does the ejecta field from such an impact look like? And how far does dangerous debris travel? According to planetary scientist Mark Robinson, the scale and effects of this crater highlight hazards that future lunar missions cannot ignore. That statement carries real weight coming from the principal investigator of the El Rossi instrument, the person who has spent more time than almost anyone else studying fresh craters on the moon's surface. He is not being alarmist. He is pointing to the kind of honest accounting that engineering and mission planning require. You cannot design a safe habitat or a reliable base without knowing what the impact environment actually looks like. And until you catch a crater of this scale, forming during a period of detailed observation, your models are based on extrapolation rather than direct evidence. The 2024 crater provides a direct data point. It anchors the models. It says, this is what happens when an object large enough to create a 225-meter crater strikes the moon. This is where the debris went. This is how far the largest blocks travelled. This is what the ejecta pattern looks like from orbit. This is what the glass formation at the centre looks like. All of that information feeds into the risk models that will inform the design of future lunar infrastructure. And this brings us to another layer of the story, one that was unfolding simultaneously with the discovery of the 2024 crater, but in a very different direction. While researchers were piecing together the aftermath of a past impact, the planetary defense community was grappling with the possibility of a future one. In late December 2024, an asteroid was discovered by the NASA-funded Asteroid Terrestrial Impact Last Alert System Station in Chile. The asteroid was designated 2024 YR4. It was first discovered 2 days after it had already passed its closest point to Earth, and it was not detected sooner because it approached Earth from the day side of the planet, from a region of the sky hidden by the bright light of the sun. Initial orbital calculations raised alarm. The asteroid appeared to have a non-trivial probability of striking Earth in 2032. Scientists moved quickly to refine its orbit, gathering more observations to narrow the uncertainty. By early 2025, the Earth impact scenario was ruled out, but something else remained. The asteroid faded from view with a lingering 4% chance of striking the Moon on the 22 December 2032. 4%. That is not a large number in absolute terms, but in the context of asteroid impact risk assessments, 4% is enormous. The standard threshold for serious concern is typically 1 in 1,000, or 0. 1%. A 4% probability is 40 times that threshold. Scientists who deal with planetary defense scenarios every day were taking this possibility seriously. Such an impact would release 5 megatons of TNT equivalent energy and produce a roughly 1 kilometer diameter crater. Estimates suggested that up to 100 million kilograms of lunar material could be liberated in such an impact by exceeding lunar escape speed. Let us let that figure breathe for a moment. 100 million kilograms of lunar rock, blasted free of the moon's gravity and dispersed into cislunar space. Not all of it would stay near the moon. Depending on the actual impact location on the moon, as much as 10% of this material may accrete to the Earth on timescales of a few days. That means roughly 10 million kilograms of lunar debris potentially arriving at Earth's vicinity within days of such an impact. For context, the Chelyabinsk meteor that exploded over Russia in February 2013 and injured approximately 1,500 people was estimated to have a mass of roughly 13 million kilograms. We are talking about comparable quantities of material, except instead of arriving as a single object, it would arrive as a diffuse cloud of smaller fragments with potentially years-long consequences for satellites in low Earth orbit. The lunar ejecta-associated particle fluents at sizes between 0, 1 and 10 millimeters could produce upwards of years to of order a decade of equivalent background meteoroid impact exposure to satellites in near-Earth space. In plain terms, such an impact could expose every satellite orbiting Earth to the equivalent of years of normal meteoroid bombardment, compressed into a short period. In an era when the global economy depends on GPS navigation, weather satellites, communications infrastructure, and military reconnaissance assets, that kind of debris environment represents a significant hazard. For comparison, similar-sized asteroids are expected to strike the Moon once every 4,000 to 5,000 years. Unlike the 225-meter crater event, which is a once-in-roughly-a-century occurrence for a given patch of ground but relatively common globally, a kilometre-scale impact would be a genuinely rare geological event, the kind of thing that would produce a crater visible from Earth with the naked eye. The astronomy community was galvanized by the possibility. Historical Apollo seismometers recorded even the approximately 1 kiloton TNT equivalent impact of the Apollo 13 SIVB stage at global distances, implying that a 2024 YR4-sized collision would produce seismic signals readily detectable across the Moon. If 2024 YR4 had struck the Moon, and active seismometers had been in place to record it, scientists would have gained an unprecedented probe of the Moon's interior structure. The waves from such an impact would travel through the Moon's entire body, revealing details about the size and composition of its core that no current mission has been able to determine. NASA pointed the James Webb Space Telescope at the asteroid in February 2026, gathering the most precise orbital data yet obtained. Using data from NASA's James Webb Space Telescope observations collected on February 18 and 26, experts from NASA's Center for Near-Earth Object Studies at the agency's Jet Propulsion Laboratory refined near-Earth asteroid 2024 YR4's orbit and ruled out a chance of lunar impact on December 22, 2032. With the new data, 2024 YR4 is expected to pass by the lunar surface at a distance of 13,200 miles. The Moon is safe for now from that particular rock. Decades of engineering, international cooperation, and innovation in the fields of science, engineering, and planetary defense culminated in the use of humankind's most powerful robotic space telescope, built by many nations to spot a distant speck of dust across the void and answer a question of universal importance to all the inhabitants of our planet. But the episode left something behind in the scientific community. A heightened awareness of the Moon as a target, not just a destination. A recognition that what happens to the Moon is not merely an academic question about a distant geological body. It is a question with direct implications for Earth, for the satellites we depend on, and for the humans we are planning to send there in the coming years and decades. The 2024 crater sits at the intersection of all of these concerns. It is a reminder that the Moon is not a static, unchanging backdrop to human civilization. It is an active participant in the ongoing dynamics of the solar system, receiving visitors of rocks and ice at intervals that are, on geological timescales, constant and inevitable. Sometimes those visitors are small, creating craters measured in meters that can be detected only with the most sensitive orbital cameras, and sometimes, roughly every century and a half for a given patch of ground, they are large enough to carve a wound 225 meters wide and 43 meters deep, throwing boulders the size of 3-story buildings across the surface and melting rock into glass with the heat of the collision. We are now watching what happens next to that wound. The Lunar Reconnaissance Orbiter continues to circle. Its cameras continue to photograph. The bright ejecta rays spreading outward from the crater are being measured and tracked. The glass at the crater floor is being analysed remotely. The dimensions and depth are being compared with impact cratering models to refine our understanding of the physics. And scientists are preparing to monitor the crater for months and years to come, watching the slow process of space weathering into something older, the bright scar, and eventually indistinguishable softer from the ancient landscape around it. That transformation, and what we can learn from watching it in real time, is exactly where we are going to go next. But first, take a step back with me for just a moment and consider the broader picture that is emerging from all of this. We have a spacecraft that has been circling the moon for 17 years, photographing its surface with sub-meter resolution, building up a library of before and after comparisons that has already identified over 200 fresh impact sites. We have the largest fresh crater ever documented during that mission, formed just over a year ago, presenting scientists with an unprecedented opportunity to study the immediate aftermath of a significant lunar impact at a level of detail never before available. We have a simultaneous scare about a future impact that prompted the use of the most powerful space telescope ever built to refine the orbit of a potentially dangerous asteroid. And we have the growing urgency of the Artemis program, which intends to put humans back on the lunar surface within the next few years, and eventually establish a permanent presence there. All of these threads converge on a single set of questions that are now more pressing than at any point since the Apollo era. What is the current impact environment of the moon? How often do rocks of various sizes strike? What happens to the surface when they do? How do the changes propagate over time? And what do all of those answers mean for the people and machines we are going to send there? The 2024 crater is not just a scientific curiosity. It is a data point in a calculation whose outcome matters enormously. It is a piece of evidence in a case that science has been building for decades. And that is now reaching a critical point as human exploration of the moon moves from aspiration to schedule. The researchers who presented this finding at the Lunar and Planetary Sciences Conference in March 2026 were careful to frame it in exactly those terms. This is not just about understanding how craters form. It is about understanding the hazard environment that any future lunar installation will have to contend with. Every number they extract from this crater, every measurement of depth and diameter and ejecta distribution and glass composition adds precision to the risk models that engineers and mission planners will use when designing the hardware and infrastructure of humanity's return to the moon. The discovery of new craters serves several scientific purposes. It helps astronomers refine estimates of current impact rates, which is essential for understanding the hazards facing both robotic missions and future human explorers. It also allows researchers to refine methods used to determine the ages of different lunar surfaces by studying how quickly craters and their features change over time. Both of those purposes are being served by the 2024 crater, and served at an unprecedented scale given the size and quality of the data available. There is also something worth noting about the human story embedded in this discovery. The scientist who presented these findings, Mark Robinson, has spent the better part of his career staring at the moon's surface. He has overseen the painstaking work of comparing tens of thousands of image pairs, looking for the tiny changes that betray a new impact. He joked at one point in a Science News interview about setting the bar with the first fresh crater his team found, a 70-metre feature that seemed large at the time, and challenging his colleagues to find something bigger. Robinson said he used to joke with colleagues that now the bar had been set. They had to find a 100-metre crater, and then, as he put it, lo and behold, they found 225 metres. There is a human quality to that moment that science does not always allow space for. The quiet persistence of years of methodical work, the accumulated expertise that trains the eye to notice the anomaly in the dataset, the particular satisfaction of having a prediction exceeded so dramatically. It is a reminder that behind every scientific discovery is a person, or more often a team of people, that most of the world attention to notice when's not looking at, and who are paying close enough attention to when something's changed. The moon changes, slowly, subtly for the most part, but unmistakably when you have the tools to see it. The 2024 crater is the most dramatic example of that change documented in the modern era of lunar science, and scientists are not done looking. They are watching what happens next. The watching, as it turns out, is itself a science. Not simply pointing a camera at the moon and recording what is there, but developing the methods, the instruments, the analytical frameworks, and the theoretical models that allow you to extract meaning from what you observe. The watching has to be interpretive. It has to be calibrated. And calibrating it is exactly what the 2024 crater is helping scientists do. Let us begin with the question of space weathering in more depth, because understanding what scientists are watching for requires understanding the process they are tracking. The phrase itself can sound abstract, almost poetic, but the chemistry and physics behind it are precise and well studied. Space weathering is the collective term for all the ways in which the harsh environment of space transforms the surface properties of airless bodies like the moon over time. On Earth, weathering means rain, wind, temperature cycles, and biological activity gradually breaking down and chemically altering rock. Limestone dissolves in rainwater. Iron oxidizes into rust. Granite cracks along mineral boundaries as water freezes and thaws inside it. The result is that the exposed surface of our planet is constantly being chemically and physically recycled, with fresh rock perpetually being exposed and old rock perpetually being broken down and transported. The moon has none of those processes. No rain, no wind, no liquid water, no biology. But it has its own version of weathering, driven by entirely different forces. At the smaller scale, each grain of regolith is likely to show damage tracks from high-energy cosmic rays, have a surface transformed by exposure to the solar wind, and be coated with vapor deposits from micrometeoroid impacts. New regolith particles are created when impact melt glass bonds together older regolith grains into particles called agglutinates. This collection of processes through which the space environment alters the moon's surface is known as space weathering. The agglutinates are particularly important. They are composite particles formed when the intense local heat of a micrometeorite strike melts the surrounding grains together with glassy material from the impact itself. Over time, the surface becomes increasingly dominated by these agglutinates, which are darker and more chemically complex than the fresh mineral grains they incorporate. The surface effectively becomes more mature in the technical vocabulary of lunar science, meaning it has been exposed to and processed by the space environment for longer. On the moon, the spectral effects of space weathering are threefold. As the lunar surface matures, it becomes darker, redder, and the depth of its diagnostic absorption bands are reduced. These effects are largely due to the presence of nanophase iron in both the agglutinates and in the accreted rims on individual grains. Nanophase iron, particles of metallic iron, just a few nanometers in size, is one of the key fingerprints of space weathering. It forms when iron-bearing minerals are reduced by the solar wind, stripped of their oxygen atoms, and left as pure metallic iron in an incredibly fine, dispersed state. These tiny particles are extraordinarily effective at absorbing light, which is why mature lunar surfaces look so dark compared to freshly exposed material. They also scatter light differently at different wavelengths, which produces the reddening effect measured by orbital spectrometers. This in situ formation mechanism is supported by numerous laboratory experiments that sought to simulate micrometeoroid impact effects, with a widely used approach employing pulsed lasers to irradiate mineral samples, simulating the intense and rapid energy deposition experienced on planetary surfaces. These experiments have successfully reproduced key features of space weathering, demonstrating the nanophase iron formation. The 2024 crater offers something that laboratory experiments, however sophisticated, cannot fully replicate: a real, full-scale, three-dimensional test case playing out under actual space conditions on the actual lunar surface. The laboratory can tell you the chemistry. The crater can tell you how fast it actually happens at the scale of hundreds of meters in the real solar wind environment, with the real flux of micrometeoroids that the Moon actually experiences. This is not a minor distinction. The rate of space weathering is one of the most contested quantities in planetary science, precisely because it's so difficult to measure directly. Laboratory experiments suggest certain timescales. Models based on crater ray brightness suggest others. Observations of asteroid surfaces, which should weather differently because of their different environments, provide a third set of constraints. Getting all of these independent lines of evidence to agree on a single coherent picture has been an ongoing challenge. The 2024 crater, with its known formation date and its high quality before and after imagery, provides a constraint that none of those other methods can match. For the first time, scientists have meter-scale photographs of a crater of this size, taken both before and after formation. That is an extraordinarily rare dataset, and one that will allow researchers to test and refine the models we use to understand how craters form not just on the Moon, but across the entire solar system. Across the entire solar system. That is not an overstatement. The principles of impact cratering are universal, governed by the same physics on every solid body in the solar system. The relationship between impactor size and crater size, the depth-diameter ratios, the distribution of ejecta, the formation of impact melt glass, all of these follow scaling laws that planetary scientists apply. When interpreting the cratered terrains of Mars, Mercury, the asteroids, the icy moons of the outer planets, and the distant dwarf planets at the edge of the solar system. When you improve the calibration of those scaling laws using a well-documented crater on the Moon, you are simultaneously improving your ability to interpret surface histories everywhere else. Consider what that means in practice. When planetary scientists look at the cratered surface of Mars and count craters in a region to estimate the age of a particular terrain, they are using a model of crater formation rates that is itself calibrated against lunar data. The Moon serves as the reference standard. We know the lunar cratering rate better than we know the cratering rate anywhere else, because we have the best orbital coverage, the most historical observations, and in the case of the Apollo samples, actual rocks from the surface dated with radiometric techniques. Everything else is derived from the lunar calibration. Making that calibration more precise and reliable improves the quality of age estimates for terrain across the solar system. The 2024 crater feeds directly into that calibration. A 225-meter crater that formed at a known time, photographed with known instruments, at a known resolution, provides a benchmark against which the models can be tested. Does the observed crater match what the scaling laws predicted for an impactor capable of leaving this kind of signature? What were the mechanical properties of the target material, and how did they influence the crater shape? How does the ejecta distribution compare to model predictions? Every question answered refines the framework that scientists use everywhere else. This is the deep scientific value of what is being observed, and it is why researchers like Mark Robinson describe this crater as a gift in scientific terms, even as they simultaneously point to the hazard implications. Science and risk assessment are two faces of the same investigation here. Now let us turn to the question of what the researchers are specifically monitoring in the months and years following the discovery. The LRO does not just take photographs. It carries a suite of instruments that measure the lunar surface in multiple ways simultaneously, and each of those instruments adds a different layer of information to the picture of how the crater is evolving. The orbiter carries a complement of instruments, including the Diviner Lunar Radiometer experiment, which measures lunar surface thermal emission to provide information for future surface operations and exploration, and the Lunar Exploration Neutron Detector, which provides measurements and creates maps of near-surface conditions. The Diviner instrument is particularly relevant to crater monitoring, because it measures surface temperatures across the entire Moon at relatively high spatial resolution. Fresh crater material, with its different texture and mineral composition compared to the surrounding mature regolith, has different thermal properties. It heats up and cools down differently under the alternating warmth and cold of the lunar day-night cycle. This thermal signature is another diagnostic tool. In Diviner data, fresh craters often stand out as thermally anomalous, retaining heat differently from their surroundings during the long lunar night. The thermal behavior is linked to the physical structure of the surface material, how large the particles are, how tightly they are packed, how much pore space exists between grains. As space weathering proceeds and the fresh ejecta is gradually processed, its thermal properties shift toward those of the surrounding mature regolith. Tracking that shift over time gives scientists yet another independent measurement of the weathering rate. The Lunar Orbiter Laser Altimeter aboard LRO adds a topographic dimension. LOLA produces a high-resolution global topographic model and geodetic framework that assists with precise targeting, safe landing, and surface mobility for future scientific and exploration activities. It makes 3 measurements: the distance between the surface and the spacecraft, the spreading of the returned laser pulse, and the transmitted and returned laser energies. For the 2024 crater, altimetry data allows scientists to measure the depth of the crater precisely, track any subsequent changes in depth as the walls begin to slump or infill with loose material, and map the topographic signature of the ejecta blanket surrounding it. Crater walls do change over time, even without erosion by wind or water. On the Moon, the primary agents of physical modification are micrometeorite bombardment, which gradually sandblasts the rim, and seismic disturbance from subsequent nearby impacts, which can cause loose material at the rim to slide down into the crater floor. These processes are slow, operating over timescales of millions of years for large craters. But for a crater this large and this fresh, the LRO instruments are sensitive enough to detect even subtle changes over periods of years. In addition to the dedicated LRO monitoring, the crater has attracted attention from the broader planetary science community. The conference presentation at the 57th Lunar and Planetary Sciences meeting effectively announced the discovery to the world, and subsequent observations by other instruments and agencies are expected to add to the data archive. The scientific value of a fresh, well-documented crater of this scale does not diminish over time. It grows as each additional dataset adds a new layer of constraint to the evolving picture. I want to take a moment here to address something that often comes up when we discuss discoveries like this, and it is worth being direct about. Some of you may have encountered coverage of this story that framed it in sensational terms, emphasizing the danger, the unexpectedness, the vulnerability of the moon, and by extension of any future human presence there. The science does not support that kind of framing. And I think it is important to be clear about what the evidence actually says versus what it implies. The 2024 crater is large by the standards of what LRO has observed during its mission. It is large enough to destroy any structure built at its impact point, and the fact that the impacting rock was not detected before it struck does represent a genuine gap in our monitoring capabilities. All of that is true and worth taking seriously. But it is also true that a 225-metre crater forms at any given patch of lunar ground only once every 139 years on average, according to the best current models. The Moon's surface area is roughly 9 million square kilometres. The probability that a crater-forming impact of this scale would strike any given planned landing site or habitat location in any given year is astronomically small, in the literal sense of that phrase. The hazard is real, but it is not acute. It is the kind of long-term statistical risk that good engineering and careful site selection can account for. This is exactly the kind of nuance that gets lost when science communication prioritizes drama over accuracy. We can discuss the significance of this discovery honestly, without overstating what it means for human safety on the Moon. The scientists themselves are careful about this distinction, and so should we be. At Deep Space Intelligence, we try to give you the full picture, the significance, the uncertainty, the context, and the caveats, rather than just the headline. I always encourage you to check the primary sources, read what the researchers actually wrote, and draw your own conclusions from the evidence. With that said, let us now turn to what might be the most forward-looking dimension of this story, what the 2024 crater means for Artemis and for the broader question of humanity's return to the Moon. The Artemis program is NASA's most ambitious lunar initiative since Apollo, and it is proceeding in a fundamentally different context than the missions of the 1960s. Apollo was a sprint, a geopolitical race driven by Cold War competition, focused on achieving the symbolic goal of putting humans on the Moon before the Soviet Union could. The science was real and valuable, but it was secondary to the mission. Artemis, by contrast, is a marathon. It is designed from the outset to establish a sustained human presence at the Moon, with scientific goals, commercial partnerships, international collaboration, and a long-term vision that extends to Mars. That long-term vision changes the calculus of risk assessment entirely. When your astronauts spend a few days on the surface and then leave, the impact hazard is essentially irrelevant on any individual mission timescale. When your habitat is going to be occupied continuously for months or years, when your equipment needs to operate reliably across solar panels and communication systems, when your self-support panels infrastructure need to function without fail, the statistical properties of the impact environment start to matter very much. The Moon has endured impacts of this scale many times over geologic history, but none have been observed in real time with modern instruments, and the discovery can help highlight the risks impacts pose to future astronauts. The specific location that NASA and its international partners have identified for the first Artemis surface missions and eventual outpost is near the lunar South Pole. This region is scientifically compelling for multiple reasons. Permanently shadowed craters at the pole are thought to harbour water ice deposited by ancient comets and preserved for billions of years in the perpetual cold of the polar darkness. Some ridgetops and elevated terrain near the pole receive near-continuous sunlight through most of the lunar year, making them ideal for solar power generation. The combination of potential water ice and reliable solar power makes the South Pole a plausible location for a self-sustaining outpost in a way that the equatorial Apollo landing sites were not. But the impact environment at the South Pole is not necessarily the same as the impact environment at lower latitudes. The geometry of how impactors approach the Moon, the distribution of impact velocities and approach angles, the local terrain that shapes the secondary ejecta distribution from any given primary impact. All of these factors vary with location. Understanding the South Pole impact environment specifically is an active area of research. And the 2024 crater, while it did not occur at the pole, contributes to the general framework of understanding that informs those regional assessments. New crater discoveries directly support NASA's Artemis program, landing site preparation efforts, and understanding crater distribution, formation rates, and hazard locations proves essential for mission safety. Beyond the immediate question of where to land and where to build, there is the deeper question of how to build. A lunar habitat designed to withstand the occasional micrometeorite strike looks different from one designed to survive within the ejecta field of a large impact several kilometers away. The engineering trade-offs depend on the probability of various scenarios, and those probabilities depend on the underlying science of impact rates and ejecta distributions. The boulders ejected by the 2024 crater offer a particularly direct input to this kind of analysis. The largest confirmed boulder in the ejecta field is approximately 13 meters across, roughly the size of a 3-story building. It landed some distance from the crater rim, carried there by the violence of the impact. In principle, a boulder of that size, travelling at the right trajectory, could be dangerous to equipment or structures within its landing zone. The question of how far such boulders travel, and with what probability, is something that the 2024 crater data can directly constrain. The previously identified record holder for a fresh crater during the LRO mission was a 229-foot-wide crater, which was discovered in 2013 by comparing before and after images of the same region on the lunar surface. That earlier record holder, now superseded by the 2024 discovery, contributed to our understanding of the impact environment for more than a decade before being exceeded. The new crater will presumably serve as the benchmark for a comparable period, providing a reference point against which future discoveries can be measured. There is an interesting historical resonance here. Humans have been making craters on the Moon deliberately, as well as observing the natural ones. The Apollo program intentionally crashed, spent rocket stages onto the Moon to create seismic signals that could be recorded by the instruments left on the surface. Historical Apollo seismometers recorded even the approximately 1 kiloton TNT equivalent impact of the Apollo 13 SIVB stage at global distances. Those deliberate impacts served as calibration tools for the seismometers, helping scientists understand how seismic waves propagate through the Moon's interior. The signals they produced revealed something unexpected. The Moon rings like a bell after an impact, with seismic energy reverberating through its dry, cold interior for much longer than similar impacts on the water-rich Earth would produce. That observation was one of the first hints of something that later research would confirm more thoroughly. The Moon's interior is profoundly different from Earth's. It is cold, rigid, and largely dry at depth, with very different mechanical properties that cause seismic waves to behave differently than they do inside our own planet. Understanding those interior properties matters enormously for the future of lunar science, because the interior holds clues to the Moon's formation and thermal history that cannot be accessed any other way. Fresh impacts like the 2024 event produce seismic signals, though the LRO spacecraft is not a seismometer and was not designed to detect them. Future missions, however, may be. Several proposed lunar surface missions in the coming years include seismometer packages as part of their scientific payloads, and some of these are specifically designed with continuous monitoring in mind. If one of those missions is in place and operating when the next large impact occurs, the scientific return could be enormous. Not just the seismic data from the impact itself, but the opportunity to correlate the seismic signal with the crater that caused it. using the kind of orbital imagery that the 2024 event demonstrated is now possible. This is one of the ongoing conversations in the lunar science community. How to build an integrated monitoring network for the Moon that combines orbital imaging, surface seismometry, thermal sensing, and direct sample analysis into a coherent observational system. Such a network would transform our ability to detect and characterize impacts in near real time, rather than discovering them months after the fact through patient image comparison. It would also serve the dual purpose of hazard monitoring for future human missions and scientific investigation of the Moon's interior and surface processes. The China National Space Administration has been an active player in lunar science in recent years, with the Chang'e series of missions achieving a series of increasingly ambitious milestones. Impact glasses found in lunar soils provide a possible window into the impact history of the inner solar system, and research using UPB isotopic dates and chemical compositions of impact glasses from the Chang'e 5 soil and quantitative models of impact melt, formation and ejection has been undertaken, with the predominantly local provenance indicated by their compositions constraining transport distances to less than approximately 150 kilometers. The Chang'e 5 mission, which returned lunar samples to Earth in December 2020, brought back material from a site that had not been sampled by Apollo. The analysis of that material, including the impact glass beads described above, is ongoing and has already produced significant results about the regional geological history of the area sampled. As China's lunar program continues with Chang'e 6 and planned future missions, including surface elements with longer operational lifetimes, the dataset available for studying the Moon's impact environment will continue to grow. The India Space Research Organisation's Chandrayaan series has similarly contributed to the global picture. Japan's Selene mission, also known as Kaguya, provided valuable multispectral and altimetry data that complements the LRO dataset. The European Space Agency has participated in lunar science through various instruments and data-sharing agreements. The Moon, in the current era, is being studied simultaneously by multiple space agencies with complementary capabilities, and the combined dataset is richer and more complete than any single agency could produce alone. Against this backdrop of growing international engagement with lunar science, the 2024 crater arrives as a case study in collaboration. The initial discovery and the detailed analysis were conducted by the LRO team. The announcement at the Lunar and Planetary Sciences Conference reached an international audience of researchers who can contribute their own analytical tools and datasets to the investigation. The crater is now part of a shared scientific record, open for examination and analysis by anyone with the expertise and interest to engage with it. This openness is one of the most valuable features of modern planetary science. The LRO data are added to the planetary data system at 3-month intervals, with a latency of no more than 6 months, and these deliveries include not only raw and calibrated data, but also higher-level data products, such as maps of geophysical quantities. The planetary data system is essentially a public archive, accessible to researchers around the world, and, increasingly, to motivated members of the public with sufficient technical skills. The images of the 2024 crater, the topographic measurements, the thermal data, all of it is going into that archive and becoming part of the permanent scientific record. There is something genuinely remarkable about that. The largest fresh lunar crater ever documented during the era of modern orbital observation sits in a publicly accessible database, available for anyone with the skills and tools to analyze it. Graduate students, independent researchers, and skilled amateurs are already examining the data. New papers will emerge from unexpected corners of the scientific community, applying analytical techniques that the original discovery team may not have thought to use. This is how science makes progress. not through the controlled release of findings from a single authoritative source, but through the open exchange of data and ideas across a broad community of investigators. Let us now talk about the geology of the crater's formation in more precise terms, because the physics of what happened in those first milliseconds after impact is genuinely extraordinary and worth exploring carefully. When an impactor strikes the surface of a planetary body, it releases a shock wave into the target rocks and the impactor itself. The shock wave puts the target rocks in motion, initiating the formation of a bowl-shaped depression known as the transient cavity. The transient cavity is the crater as it exists in the first fractions of a second after contact, before the material has had time to respond to the sudden pressure and begin flowing. It is the primary excavation, the hole carved directly by the passage of the shock wave. In that first instant, the shock pressure at the point of contact can reach millions of atmospheres, far exceeding the yield strength of any geological material. Rock behaves like a fluid under those conditions. It does not fracture in the normal sense. It flows. The shock wave propagates outward and downward into the target at speeds that initially exceed the speed of sound in the rock, creating a zone of intense compression. Behind the shock front, the rock rebounds explosively as the pressure drops. This rebound is what launches the ejecta upward and outward. The deeper and slower material forms the base and walls of the crater, the uppermost material, closest to the point of contact and hit first by the shock wave, is launched at the highest velocities. Some of it is vaporized entirely. Some is melted. Some is fractured and thrown outward as solid fragments of varying sizes. Some of the ejecta may be large enough to cause secondary craters when it crashes back to the surface, and these smaller craters will later be seen as chains or clusters of craters pointing back to the main crater. Most of the ejecta spreads out in the area around the crater, thicker and more uniform nearest the crater. Plumes of ejecta that settle back onto the surface form the bright rays seen radiating from many of the Moon's craters, and a portion of the ejecta may even reach orbit, as evidenced by lunar meteorites found on Earth. That last point is one of the most fascinating implications of large lunar impacts. Lunar meteorites, rocks from the Moon that were ejected by impacts and eventually landed on Earth after travelling through interplanetary space, are a real and well-documented class of material. Several hundred have been identified, mostly discovered in the Antarctic ice fields, where the contrast between the pale rock and the dark ice makes them easier to spot. They are chemically identical to Apollo samples from comparable lunar geological units, confirming their origin. The 2024 impact, given its scale, certainly ejected some material at speeds exceeding lunar escape velocity. Most of that material dispersed into interplanetary space, but a fraction of it may eventually arrive at Earth. In the fullness of time, on timescales of thousands to millions of years, some of the rock thrown out of the 2024 crater may fall to Earth as meteorites. The idea that a piece of the scar we are discussing tonight might one day be picked up off a glacier in Antarctica, studied in a laboratory, and dated to the spring of 2024, is not science fiction. It is a straightforward implication of the physics. The secondary craters mentioned above are another dimension of the 2024 event that scientists are examining. When large ejecta blocks land beyond the primary crater, they do not just sit there. They impact the surface at sufficient velocity to create their own craters, smaller than the primary, but still significant. The distribution of these secondary craters around the primary provides additional information about the ejection velocity distribution and the size distribution of the ejected material. Mapping the secondary crater field around the 2024 impact is part of the ongoing analysis. Lunar regolith is primarily formed by continuous impacts of large and small meteoroids with the lunar surface. Other processes such as volcanic eruption and thermal fatigue may make a minor contribution to regolith generation as well. Serving as the boundary between the solid moon and the space environment, lunar regolith not only preserves key information about lunar geology, but also provides critical records for the history of the inner solar system impact flux, the solar wind, and galactic cosmic rays. The regolith itself, that blanket of pulverized, processed rock that covers the entire lunar surface to varying depths, is essentially the cumulative product of billions of years of impacts like this one, just at a smaller scale on average. The 2024 crater is unusual in its size, but it is contributing to the same process that has been building the regolith layer since the moon formed. Every impact, however small, grinds a bit more rock into dust, mixes a bit more material, and deepens the layer of processed, space-weathered material that separates the pristine bedrock below from the open space above. The depth of the regolith varies considerably across the lunar surface, ranging from a few meters in the mare regions, where ancient lava flows provided a relatively hard substrate for subsequent impacts to grind against, to tens of meters in some highland regions where the bombardment history has been longer and more intense. The 2024 crater, at its formation site near the Highland-Mare boundary, cut through whatever regolith existed there and penetrated into the underlying solid rock, which explains the steep walls and the glassy impact melt at the floor. The materials it excavated and threw outward reflect the layered structure of that particular piece of the moon. Older, weathered surface material on top, fresher bedrock below. One of the analytical techniques that researchers will apply to the crater over time is spectroscopy from orbit, using instruments that measure how the surface reflects light at different wavelengths to determine the mineralogy of the exposed material. Space weathering processes form submicroscopic metallic iron particles that are optically active, darkening and reddening the lunar surface over time, with the optical effects depending on their size, with nanophase iron darkening and reddening, while microphase iron darkens without reddening. By tracking how the spectral signature of the crater and its surrounding ejecta changes over time, scientists can measure the rate at which these iron particles are forming, which is directly related to the rate of space weathering. The crater effectively resets the spectral clock to 0 at the moment of formation. Everything inside the ejecta blanket starts as fresh, unweathered material, and then ages in real time under the sun's continuous bombardment. This kind of long-term spectral monitoring is only possible because LRO has been operating continuously for so long and is expected to continue operating for the foreseeable future. Every year of continued observation adds another data point to the time series. In 5 years, the researchers will have a record of how much the crater has changed in 5 years. In 10 years, 10 years of change, that temporal baseline is enormously valuable and impossible to replicate by any other means. There is a broader context here that is worth making explicit. We are living in a golden age of lunar science. The combination of the LRO's sustained orbital campaign, the sample return missions of recent years, the proliferation of international lunar missions, and the renewed human exploration program has created a richness of data about the moon that was unimaginable a generation ago. The questions that planetary scientists are now asking and beginning to answer about the lunar impact environment, the distribution of surface resources, the geology of the poles, and the history of the inner solar system as recorded in lunar rocks, are questions that could not have been seriously addressed with the tools available even 20 years ago. The 2024 crater is one piece of this larger picture, but it is an unusually revealing piece, precisely because of its rarity and its timing. It formed at a moment when we had the instrumentation to document it properly. It formed at a scale large enough to be unambiguous and scientifically rich. And it formed during a period of renewed interest in the moon's practical utility for human exploration, giving the pure science of impact, cratering an immediate applied relevance that it might not have had in an earlier era. Scientists are watching the crater partly out of pure intellectual curiosity, because new craters are inherently interesting, and this one is exceptional. They are also watching it because the data it generates feeds into models that have direct engineering consequences, and they are watching it because it is a reminder of something that can be easy to lose sight of when space exploration is reduced to launch schedules and budget discussions. The solar system is alive, not biologically alive, but dynamically alive, constantly in motion, with rocks of all sizes, following orbits that occasionally intersect with the surfaces of solid bodies, including the Moon, including Earth. The 2024 crater is a reminder that we are embedded in that dynamic system. We are not observers watching it from a safe distance. We are participants. The rock that carved that 225-meter wound into the lunar surface was travelling through the same neighbourhood of the solar system that Earth occupies. It struck the Moon rather than the Earth. But the physics that determined that outcome was simply the geometry of its particular orbit at a particular moment in time. A different orbit, a different arrival time, and the energy would have been deposited somewhere else. This is not alarmism. The probability of any given rock striking Earth is small, and the planetary defense community is actively working to improve our ability to detect and, if necessary, deflect objects that might pose a genuine threat. NASA's DART mission successfully demonstrated in 2022 that a kinetic impactor can meaningfully alter the orbit of a small asteroid. That capability is now a reality, not just a theoretical possibility, but the vigilance that planetary defense requires, and the humility about what we still do not know about the population of near-Earth objects are both reinforced by events like the 2024 crater and the 2024 YR4 episode. The YR4 episode in particular was instructive in a specific way. It showed how quickly scientific uncertainty can be resolved when the community mobilizes its best tools. The James Webb Space Telescope was not designed or intended for planetary defense work. It is an infrared observatory optimized for studying the most distant objects in the universe, from the earliest galaxies to the atmospheres of exoplanets. Yet, when the planetary defense community needed the most precise orbital measurement possible for a faint, distant asteroid, Webb was redirected to do exactly that. Decades of engineering, international cooperation, and innovation culminated in the use of humankind's most powerful robotic space telescope to spot a distant speck of dust across the void and answer a question of universal importance to all the inhabitants of our planet. That flexibility, that willingness to use any available tool to address an urgent scientific question, is one of the strengths of modern space science. The same adaptability will be needed as humanity expands its presence at the Moon. New instruments, new monitoring capabilities, new analytical methods will be brought to bear on the question of the impact environment, and the picture will continue to sharpen. There is one more dimension of the 2024 crater story that deserves attention before we bring this investigation toward its conclusion. And it connects the specific science of this crater to the deepest questions in planetary science. It concerns what the impact record preserved in the Moon's surface can tell us about the history of the entire inner solar system. The Moon, as I noted earlier, is a record. Every crater on its surface is a timestamp, a mark left by a collision whose energy, direction, and timing are potentially recoverable from the physical evidence if you have the right tools. The accumulated crater record, read correctly, tells the story of how the population of solar system debris has evolved over time. During the late heavy bombardment, the flux of large impactors was dramatically higher than today. Since then, it has been declining, with occasional spikes associated with specific events in the asteroid belt, where collisions between larger bodies created fresh populations of debris that eventually found their way to the inner solar system. Understanding that history helps astronomers understand the broader evolution of the solar system. It places constraints on the dynamical models that describe how the planets migrated to their current positions, how the asteroid belt was sculpted by Jupiter's gravity, and how the early bombardment history of Earth influenced the conditions under which life arose. These are among the most profound questions in planetary science, and the Moon sits at the centre of them. Every new, precisely dated impact, like the 2024 crater, adds a data point to the calibration of the chronological framework that underlies this entire investigation. The more precisely we understand the current impact rate, the more confidently we can extrapolate backward to reconstruct the ancient impact history. The more accurately we can date specific craters, using the kind of space weathering observations that the 2024 crater enables, the more reliable the timeline of solar system history becomes. The Moon is not a static object. The surface we have looked at for generations continues to evolve, gaining new features as it travels through space. Fresh craters are a reminder that the Moon is still being shaped by ongoing impacts, and that the solar system remains active and occasionally violent. That observation is both scientifically precise and philosophically resonant. The Moon we see when we look up at the sky tonight is not the Moon that existed yesterday, not in the strict physical sense. It is a body that is being continuously shaped by its environment, accumulating new scars at a rate that is measurable and documented. The face we see is ancient, yes, but it is also a work in progress, still being written by the ongoing story of our solar system. The 2024 crater is the most recent chapter in that story, visible to us from Earth. In the orbital imagery from LRO, it sits as a bright, sharp-edged wound against the darker surrounding terrain, its ejecta rays extending outward like the spokes of a wheel, its floor dark with the glassy residue of unimaginable heat. In 1,000 years, if the records of our civilization survive, a scientist will look at images of that same location and see something softer, dimmer, less distinct. The rays will have faded as space weathering works its slow chemistry on the exposed material. The sharp rim will have been rounded by the patient sandblasting of micrometeorites. The glass on the floor will have been incorporated into the regolith layer, churned and reworked by countless smaller impacts. In 1,000,000 years, the crater will still be there, still detectably younger than the terrain immediately around it, by the subtlety of its brightness and the slight freshness of its mineralogy. In 1,000,000,000 years, it will be indistinguishable from the ancient surface that surrounds it, absorbed into the accumulated record of all the impacts that have shaped that particular piece of the Moon over geological time. The story of the 2024 collision will persist in the rock, but it will take ever more sophisticated tools to read it. We are living in the brief window when the story is still loud and clear and freshly written, when the orbital cameras can see it in sharp relief, when the before and after comparison is unambiguous, when the ejecta rays are still brilliant with the brightness of freshly excavated material. This is the window scientists are working in right now, gathering as much data as possible, while the evidence is at its most legible. The LRO team will continue to pass over the crater on every orbital period, logging small incremental changes across successive passes. The data will continue to accumulate in the planetary data system, accessible to researchers worldwide. Papers will continue to appear in journals like Icarus, the Journal of Geophysical Research, Planets, and the Planetary Science Journal, each adding a new analytical layer to the understanding of what this crater is and what it tells us. And at some point, perhaps years from now, the accumulated picture will be complete enough to write the definitive paper on what happened in the spring of 2024 on that patch of lunar ground near the boundary between the Highland and the Mare. The impactor will be characterized as precisely as the data allows. The cratering mechanics will be fully reconstructed. The rates of space weathering observable in the imagery will be compared to predictions and used to refine the theoretical models. The hazard implications will be quantified and incorporated into the planning documents for Artemis and successor programs. That paper will sit in the archive alongside all the others, one more contribution to humanity's growing knowledge of the solar system we inhabit. But behind that paper, behind all the data and the models and the analytical frameworks, is a simple fact that I find genuinely moving in its starkness. Something hit the moon. In the late spring of 2024, a rock that had been travelling through the solar system for perhaps billions of years, following an orbit shaped by the gravitational influences of planets it had never come close to, arrived at the moon's surface at extraordinary speed and released its energy in an instant. The rock ceased to exist as a rock. The material of the moon's surface was transformed violently and irreversibly. A hole 225 metres wide and 43 metres deep was carved into a landscape that had been relatively unchanged for millennia. Boulders the size of buildings were thrown outward in all directions. Glass was created from rock in temperatures hotter than the surface of the sun, and nobody saw it happen. We are only now, months later, piecing together the story from the evidence left behind, the way forensic scientists reconstruct an event from its aftermath. The LRO camera is our microscope, the orbital imagery our evidence archive, the scaling laws and impact physics, models our analytical tool, and the picture that emerges, painstakingly assembled from all of these pieces, is a portrait of the moon as it really is, not the static, ancient, unchanging world of poetry and legend, but a dynamic, active body still being sculpted by its violent past and its violent present, carrying on its face the record of everything the solar system has thrown at it across 4.5 billion years. Scientists are watching what happens next to that scar. They will keep watching, and what they learn from watching will help us understand not just the moon, but our entire neighbourhood in space, and ultimately ourselves, small and brief and curious, perched on a planet that sits in the same solar system as every rock that has ever struck the moon, breathing an atmosphere that shields us from the same bombardment that has left those marks, looking up at the night sky with instruments that let us see, for the first time in human history, the cosmos as it truly is. That is the story of the 2024 lunar crater. It is a story about a rock and a hole in the ground. It is also a story about how science works, about how observation and theory and patient analysis combine to reveal truths that no individual human being could perceive alone. It is a story about the moon as a place, not just as a symbol or a destination, but as a real geological body with a complex and continuing history. And it is a story about where humanity is headed, toward that cratered surface, with all its hazards and all its scientific riches, because the questions we can answer by going there are questions worth answering. Thank you for spending this time with me on Deep Space Intelligence. The science here is ongoing, the data is still being gathered, and the papers are still being written. As always, I encourage you to go further, to read the primary sources, to examine the imagery for yourself, and to follow the work of the researchers at the Lunar Reconnaissance Orbiter camera team and the broader planetary science community who are doing this work. The links and references connected to this episode will give you a starting point. Where you go from there is up to you. That, ultimately, is what this channel is about. Not just telling you what scientists have found, but giving you the context and the tools to engage with those findings critically, thoughtfully, and with the kind of intellectual curiosity that makes science not just a body of knowledge, but a living practice. Stay curious, keep asking questions, and we will see you on the next one.